Good morning, good afternoon, sorry. So we continue with step 2. The slide is ready in ellipse. The first step is there's a 5 step to conduct MPA, mass pinch analysis. The first step is plan audit on mesh network. So we have MTB and another one, mesh transfer based operation and non-transfer based operation. So this week we continue with data extraction. I'm using what is it? Water pinch analysis for water management and minimization by Sharifah Rafidah Wad Alwi and Zaiduddin Abdul Manan from UTM. Handbook of Process Integration. The process chosen are preferably close geographically and are also chemically related. The main contaminant that prevent direct use in the water system are chosen. The system can be modeled either as a single contaminant or multiple contaminant approach based on the water quality requirement of the plant process. However, there's a problem with multi-contaminant, which involve complex modeling procedure and relies on modeling and optimization technique. So to simulate the contaminant is to use the aggregated contaminants such as suspended solid and total dissolved solid (TDS), which allow multiple quality factor to be modeled in the single contaminant approach. So what important of data extraction, the entire water resource and sink flow rate and quality requirement for each water using process are extracted. All of it, this is from the process. The water source data are obtained by identifying the maximum concentration limit and the minimum flow rate limit of the wastewater source from each process. The water sinks data are usually obtained from historical variation, emergency water substitution, estimate from engineers, vendor, and operator, and description in equipment list. So before we proceed, you need to know what is source and sink. Okay. Water sink is what inlet for any process. Water source is outlet from it. That's all. Yeah. Sink is in, source is out. Therefore, water source data from the unit operation can be obtained by identifying the maximum concentration limit and the minimum flow rate limit of the wastewater source from each process. The water sinks fit to the process or the unit operation are obtained from historical operation, emergency water substitution estimates from engineers, vendors, and operators, and description in equipment list. Step 3, setting the minimum utility target. There are actually have 6 methods, only cover 3 of it. Limiting composite curve LCC. Water using processes are plotted on a concentration versus flow rate diagram only applicable for the fixed flow rate problem. Or in other words, is for MTB problem only. Water cascade analysis WCA, a numerical version of water surplus diagram by Halale that eliminate the iterative process and provide a more accurate result. The last one is source sink composite curve. Water source and sink are plotted on a contaminant mass load versus flow rate diagram. Limiting composite curve LCC is applicable for MTB operation, mass transfer based operation. Each water using process is assumed to have fixed flow rate. There is a transfer of mass load from process stream 1 to process stream 2. Each process stream that has an inlet contaminant and outlet contaminant concentration is plotted on the LCC. This is the example of LCC composite curve. This is a MPA mass pinch analysis. So the pinch is where the graph in contact, I think, with the freshwater supply line. The stream are then composited according to the concentration interval. So the data is from the process. A limiting freshwater supply line is drawn from origin 0 and mass load with a slope that just touches the composite curve. This gives the minimum flow rate target for the system. The point where the supply line and composite curve touch is termed the pinch point. This is the pinch point. Sourcing composite curve. The sourcing composite curve is used to target the minimum usage of fresh resources for material recycle or reuse network. 5 key steps to construct the curve in terms of the water system. This is the 5 step. Rank the sink in ascending order. So sink is inlet, source is outlet. Rank the sink in ascending order of maximum allowable contaminant concentration. Rank the source in ascending order of maximum allowable contaminant concentration. We need to plot the sink and the source. Plot the maximum mass load of each sink versus its flow rate. Create a sink composite curve by superimposing the sink arrow in ascending order. Plot the mass load of each source. The rank the source in ascending order is based on the ascending order of maximum allowable contaminant concentration. Then you plot the source composite curve. After that, once you plot it, shift the source composite stream until it touches the sink composite stream with the source composite curve. So the source composite curve, it to shift it until it overlap the sink like this. Once it's overlap, that is the pinch point. This is the second method. For the second method, the gap here is the fresh water, yeah, without the source. Because sink is feed and source is the outlet. So the later part, this region is wastewater. It consists of only a source. This is the optimum flow rate for freshwater and wastewater. The minimum freshwater target is that flow rate of sink below which there are no sources on the left hand side. The minimum wastewater generation target is the flow rate of sources above which there are no sink on the right hand side. Okay. Process modification. Process modification are changes made to the individual water using operation to modify either the flow rate or concentration of water source or sink. The appropriate steps to modify a process depend on the location of the water source and sink. Relative relative to the pinch point of the system. This is the pinch point where the source curve and sink curve overlap. So above the pinch, this region, beneficial changes can ay, can be achieved by either increasing the flow rate or water purity of a source or by decreasing the flow rate or water purity requirement of a sink, thus increasing the water surplus above the pinch. and thus the amount of fresh water required will be reduced. This is for above the pinch. The beneficial changes is to increase the flow rate or water purity, because this is wastewater of a sink, meaning you purify the above the pinch to be reused by the sink. Right? Okay. For below the pinch, there is already a surplus of water below the pinch. Hence, any flow rate changes made there will not affect the target. An exception to this rule of thumb is for the case where source purity is increased so that it moves to the region above the pinch, as in the case of regeneration. At the pinch point, increasing the flow rate of the source at the pinch concentration will reduce the target. So another scope for process modification, the purpose is to reduce the water target. The purpose is to reduce the water target, hence water consumption. So the two method is water regeneration and equipment modification. For equipment modification, equipment is usually modified in order to eliminate or reduce water using operation. Water elimination may involve eliminating one of the water sink. For example, using alternative cooling media such as air instead of water. Water reduction involves changing the process equipment into one that uses less water. For example, water saving toilet flushing system, which reduce the water sink's flow rate. So for equipment modification, it's either eliminate or reduce the water using operation. This is the example. For water regeneration, it involves the partial or total upgrading of water purity using purification techniques such as filtration, gravity settling, activated carbon, membrane, and biological treatment. So the regenerated water source will have a higher water quality. This technique can be used in isolation or combination. For example, filtration might be essential before a membrane to prevent membrane falling. Water regeneration. Okay. Use of water regeneration, water composite curve, and the pinch purity to guide the regeneration of water source as follow. Regeneration above the pinch point. The water source, this is the guideline for regeneration above the pinch. Water source in the region above the pinch are partially treated to upgrade the water purity. Regeneration across the pinch. Water source in the region below the pinch are partially treated to achieve purity higher than the pinch purity. Regeneration below the pinch water source in the region below the pinch are partially treated to upgrade purity. However, the resulting water source is still maintained below the pinch. This is just a guideline how to regenerate the strategy to generate the water. Note that regeneration above and across the pinch will reduce freshwater consumption, water generation, while regeneration below the pinch will only reduce wastewater generation. The fourth step for conducting the mass pinch analysis. For water recovery network, there are three important heuristics. First, do not feed water source above the pinch, including fresh water, to sink below the pinch and vice versa. This is just a rule of thumb to follow. It has to be noted that in order to achieve freshwater and wastewater flow rate target, it is necessary to observe the pinch division. The water source above the pinch, including freshwater, may not fit sink below the pinch and may not mix with sources that are below the pinch concentration and vice versa. Second one, start the source sink matching process with the sink at the lowest contaminant concentration. After all the sink and source has been separated according to the pinch division, above and below pinch concentration, the source sink matching process is carried out. All the sink and sources in the water utilization network will be mixed according to their contaminant constraint. The sink with lowest contaminant concentration is first matched with the source with the lowest contaminant concentration. The quantity of water from the contaminated source that will be required to provide the contamination load associated with the sink is determined by mass load contamination delta M for each sink. Contamination load for an operation can be calculated as follows. So at the end, the unit is ton per hour. So ppm here is part per million. So 1/1 million is not similar to ppm equal to milligram per liter. Heuristic 3 map the available sources one after the other and add fresh water as required to each sink according to heuristic 2 until all sinks have been satisfied in terms of both quality and quantity. One of the method is sourcing allocation composite curve. Sourcing allocation composite curve can be used to show the water network allocation or design between the source and sink. In constructing a source and sink allocation composite curve, El-Halwagi proposed the following step where the authors assume fresh water has zero mass load. So the assumption is fresh water has zero mass load. Although you use the fresh water, M is 0 equal to 0. This is the composite curve. SK1 refer to sink, SR is source, FW is fresh water, M is mass load. See, based on the assumption there is no fresh water load. The x-axis is flow rate in ton per hour. Satisfy a sink using the water source. If the sink, if the sink mass load is met, but not the flow rate, add fresh water. For example, in figure 10.12, sink 1, flow rate can be satisfied by part of source 1 and also by freshwater flow rate of SK1. See here, SK1. So SK1 is comprises of flow rate from SR1 and FW, freshwater. The mass load is fulfilled by MSR1 SK1 and MFW SK1. Sink 2, for example. This is sink 2. Flow rate is satisfied by the remainder of source 1. Remainder of source 1. And so this is part of source 1, the remainder. Only in this case it is a shift to the right. Therefore, sink 2 flow rate is satisfied by the remainder of source 1, FS, FSR1, part of source 2, FSR2, SK2, and FW SK2 freshwater. So SK2 is comprises of freshwater source 1 and source 2, part of the source 2, and the remainder of source 1. The procedure is repeated until all sinks have been satisfied by the available source and fresh water. The mass load allocation for each sink is as shown on the y-axis of the graph, and the flow rate allocation is presented on the x-axis. Similar to SK3. So in this case, SK3 here is comprises of reminder as source 2 and sum of source 3. See here? Uh, wait. Okay, SK3. So SK3 is comprises of remainder of source 2 and sum source 3. So after the SK3, most of the SR source tree will is the wastewater. Yeah, it's a wastewater. So for wastewater, because it is above the pinch, sorry, because it is above the pinch, based on the based on the Halale proposal, the water composite curve and pinch purity for above the pinch, we can partially treated the SR3 wastewater, remainder of SR3, sorry, to upgrade the water purity. Okay. Uh, Mass load deficit case. The mass load deficit case is proposed by Wan Alwi and Manan from UTM. They propose it because the previous method by Poly and El Halwagi, which using cleanest to cleanest matching rule, only cater for flow rate. Only cater for flow rate deficit case. The case where the mass load of a sink is satisfied but not its flow rate is shown. Dah kah? Oh, okay. There is another important case which is the mass load deficit case where the source meet only the flow rate of the sink but not the mass load. Therefore, using the cleanest source does not meet the mass load of a sink result in an excess mass load of source and ultimately an unsatisfied flow rate for subsequent sink. Hence the mass load deficit case. So Wan Alwi and Manan propose to satisfy the mass load and flow rate of a sink using the cleanest as well as the dirtiest source in the pinch region, making sure the pinch point and utility target are satisfied. And they come up with the network allocation diagram, which translate the source and sink location composite curve into a network mapping diagram for easy visualization. This is the example of network allocation diagram. It's look complicated, but it's actually easier to understand. For example, SK1, this is SK1. So SK1 here comprises of source 1, fresh water, and source 2. See here? Source 2. So how much is fresh water here? It's only 5 ton per hour. For S source 1, it's 50 ton per hour. And for source 2, it is partial source 2 is only 15 ton per hour. So SK1 have fresh water, source 1 and partial source 2. How about SK2, sink 2? It comprises of only fresh water. Yeah, only fresh water. So 70 ton per hour of fresh water. For SK3 here, it comprises of remainder uh, SR2 and part of S source 3. So 60 source 2 and 40 source 3, while the remainder of source 3 become the wastewater. This is a network allocation diagram in AD. The last step for mass pinch analysis is economic evaluation. Most authors resort to complex mathematical modeling in order to calculate the network cost, detailed piping routing, and geographical constraint associated fixed and variable costs. For preliminary economic calculation, payback period is widely used as a criterion to assess the feasibility of a proposed network solution. The payback period is calculated as follow: net capital investment over net annual saving. So net capital investment is the investment needed for pipe rerouting, pumping, storage tank, for intermittent processes and control systems. The net annual savings is the amount of saving that result from freshwater reduction. Okay. Water pinch technology, the first problem. Uh, this is the example. A certain process contains several water processing operations as shown in table 10.22. Create the limiting composite curve LCC by plotting the contaminant concentration C against contaminant load. Calculate the minimum water flow rate for maximum reuse. For the first, there are four operations. This is contaminant flow rate, concentration in, concentration out, limiting flow rate. So to solve this uh, problem, plot the limiting water profile first. For example, operation 1 with contaminant flow rate 2 kilogram per hour here. So it start from 0 to 100 ppm. The second operation start from 50 to 100 pm. So the contaminant flow rate is increasing. So from 2 plus 5 is 7, then 37, 41. For the third operation starting from 50 to 800, see here. Then the last operation is from 400 to 800 ppm. After that, you need to combine the limiting water profile for problem 8a. So the dotted arrow here represent the actual limiting water profile. But for the combine, we follow the uh, C in and C out. So here C in, C in, C in is what should it, 50 to 100, 0 to 50 to 100, then 100 to 400, 400 to 800. This is the combined limiting water profile. Then you plot one line, water supply line from the origin and tangent to the pinch. Therefore, this is your pinch point. So answer to B, calculate the minimum water flow rate for maximum reuse. The minimum flow rate equal to mass pickup at pinch. Mass pickup at pinch is 9 kilogram per hour. Here, over 100 ppm. So ppm is not milligram per liter, it's 1 over 1 million. So you get at the end 90 ton per hour. This is the minimum flow rate for maximum reuse. This for your exercise. So first you need to create the LCC by plotting the contaminant concentration versus contaminant load based on the C in, C out and contaminant flow rate. After that, you can get the pinch after you, right? After you draw the water supply line. So this book is it done? Sustainability in the process industry integration optimization. I think this is part of the textbook use. Mm, 249. Better. Okay. This is the example before. And for the water pinch technology, the second problem, using the stream data from problem 8, can refer to the slide. Suggest a design of a network for maximum reuse of water. The limiting CC is shown in figure 10.32. I wait. Okay. So I will share with you the book after class. Problem 9. Okay. So the solution is cut off the pocket of the limiting CC. The minimum water requirement for each pocket can then be defined for each region. This is the pocket. This enable to proposal for the design strategy shown in 1034. This is your design strategy. Following the design strategy, set up a design grid in 1035. Connect stream to water main and merge operation that cross boundary. Then connect operation directly as shown in 1038. Sorry. Remove intermediate in 1037. Then connect operation directly as shown in 1038. Finally, figure 1039 is straight in conventional flow sheet from one of the possible resulting design of the water. Okay, start from the beginning. This is the limiting composite curve from previous problem. So you cluster it into two pockets. So to calculate 45.7 ton per hour, you need to get 45.7, need to 41 minus 9 over 800 minus 100. 800 is here, 100 is here. Then turn it to ton per hour means you need to times 1,000 here. Then you get 45.7. The water pinch, okay. Okay. So this is the design strategy. So you have 90 ton per hour in, then out. Should be 90 ton per hour. It's a mass balance. Then you use 45.7 ton per hour, 100 ppm for the next process. The 44.3 ton per hour is the excess. This design grid for water system is based on the limiting flow rate. So limiting flow rate, if you refer to the slide, operation one have 20 ton per hour. Operation two is 100. It's a last column, the fifth column. Sorry. 40 ton per hour for operation three. So and so on. This is the limiting flow rate. For the flow rate, for the interval is 90 ton per hour is a feet. So in this case, fresh water. So one is straight to the second second pocket with number two is the second operation, which is 50 ppm. The third also 50 ppm in. I refer back to the table in the slide number 40, table 10.22. From here, 90 minus 45.7 is 44.3 ton per hour. This is the wastewater. Then 4 is 400 ppm into the last, we call what we call it, grid. So 0 ton per hour at 100 ppm. Based on the, on here, so 45.7 is the wastewater. Next, connect stream to water main and merge operation that cross boundary. This is based on the limiting flow rate. First is freshwater 90 ton per hour. We have limiting flow rate for first operation is 20 ton per hour. For the second is 50 ton per hour. For the third one is 20 ton per hour in. And for the next part is 40 ton per hour. Operation 3 here, see? Because this is a mass balance, it should be similar. And for the last part is 5.7 ton power for operation 4. Remove remove intermediate water main where this is appropriate, 10.37. Then okay. So remove the intermediate water main, then connecting source. So intermediate is in the middle. So this is the direct connecting operation directly. So this is the direct operation without the intermediate. So from 90 ton per hour fresh water to 45.7 ton per hour and 44.3 ton per hour both are wastewater. Flowsheet representation of a water system design, because this question asking about uh, design, suggest a design of a network for maximum use of water. So from fresh water 90 ton, 20 ton per hour going to operation 1, 50 ton per hour going to operation 2, then 20 ton from the 90 ton fresh water go straight to operation 3 using add up water after operation 1. For operation 2, 5.7 goes to operation 4, while the 44.3 ton per hour straight to the wastewater. So this is the uh, design network for maximum reuse of water for 90 ton per hour fresh water. Then case study. Go straight to case study. So far we have learned the step to conduct mass pinch analysis. Then example how to do it. And based on the course plan here, this week I need to wait. Need to present a case study as well. This is mass bench analysis. There's a further application of process integration, including hydrogen network, oxygen pinch analysis, combined analysis, energy, water, oxygen, water, and pinch emergy. Sorry, energy. Yeah, emergy. Pinch emergy. Emergy is embodied energy. Okay. So, so this book is Handbook of Process Integration. I will share with you later. Chapter 10. Example of successful case study. Water pinch analysis have been WPA's water pinch analysis has been implemented has been implemented in various industry which consume a high amount of fresh water and produce wastewater. Oops. Such as semiconductor, chloro, chloral alkali, paper mill, palm oil, refinery, food industry. Example of an application of water pinch analysis on a tire to fuel case study described by Noruddin and Helwagi. Figure 10.6, this is figure 10.6, 10.16, show a tire to fuel process. Scrap tire are converted into gases and liquid fuel via pyrolysis. So what is different between pyrolysis and gasification? Pyrolysis means you need to inject inert gas during the pyrolysis to prevent the material from turning to ash, which is to eliminate the presence of oxygen inside the reactor. Gasification is without the injection of inert gas. It's the difference between pyrolysis and gasification. So from this tire to fuel process, later. Mm, that okay. Water jet shredding. Oh, tire is added to water jet shredding, and shredded tire is goes to pyrolysis reactor. The water will go straight to tire. Water for water jet shredding go to filtration. The wet cake to solid waste handling. The fresh water is 0.1 kilogram per second to compression. Then 0.18 will go back to the water jet shredding plus fresh water. And then the liquid oil goes to separation while the reactor of gases is condensed. The gaseous fuel, then decanter wastewater 0.2 kilogram per second. The light oil is goes back to the separation, then finishing. So the fresh water is added into the seal pot, so then flare and to atmosphere. This is the process for tire to fuel process. Ish. Okay. From the process, it can be observed that there are two wastewater streams with potential as water source effluent from the decanter and seal pot, and two water sink, seal pot, and water jet compression station. Heavy organic content was identified as the main contaminant as the main contaminant concentration for this process. The following flow rate and contaminant concentration constraints were identified for the water sink. So the seal pot 0.1. Seal pot. So seal pot is here. Eh, yeah, seal pot. Okay. 0.1 kilogram per second. Sink. Flow rate of the feed water and less than 0.2. Impurity concentration of feed water PM from 0 to 500. Make up to water jet compression. For the water jet shredding, the flow rate is of feed water is 0.18 to 0.2. Impurity concentration of makeup water is 0 to 50 ppm. On the other hand, the water source have the following operating condition. Decanter wastewater flow rate equal to 0.2 kilogram per second. Purity concentration is 500 ppm. Seal pot wastewater flow rate equal to flow rate of feed water sink. Impurities concentration equal to 102 ppm. So this is the NAD. This is the sourcing allocation curve. How to wait, how to draw this? It's based on the 0 to 500. Oh, they didn't provide the data. Actually, you need C in and C out here. So for SK1 from 0 to 10 here, mass lot. Oh, 9, don't know. So this is from the data, they didn't provide it. Then the NAD is below the sourcing allocation curve. So SK1 here, this is a good method, NAD. NAD stand for network allocation diagram. This one is network allocation diagram. So SK1 is most, yeah, it's fresh water, 0.135 kilogram per second, here per second, fresh water. While SK, eh, wait, SK1 is comprised of source 1 as well. Clear lah. SK1, okay. Partial source 1. So source 1 for SK1, sink 1 here is 0.045 kilogram per second. For SK2, sink 2, it's source 1 and source partial, remainder of source 1 and partial of source 2. Silap ni. So source 1 is 0.055 kilogram per second. while source 2 is 0.045 kilogram per second. And the remainder of source 2 is wastewater. Yeah. The limiting water data for tire the fuel case study flow rate. Oh, flow rate, okay. As described in section 10.32. As described in section 10.32, which is 10.32 refer to data extraction, step 2. The maximum contaminant concentration and minimum flow rate should be selected for the limiting water data. The limiting water data for this process are summarized in table 10.3. Okay. Figure 10.7a shows the sourcing composite curve which give the minimum freshwater flow rate. Freshwater flow rate of 0.135 kilogram per second and minimum wastewater flow rate is 0.155 kilograms per second. This represents a significant flow reduction of 51.8 and 48.3% for freshwater and wastewater. Since this is a very simple problem, the same 10.7a also represents the sourcing allocation curve. The picture below the curve shows the NAD network allocation diagram for the process. The final network is illustrated in figure 10.18. So after the pinch, wait, oh, I, okay. So after the pinch, the dotted line is the reuse. There is no regeneration. Fresh water are added for the feed to water jet shedding. Water from decanter 0.155 is added to flare. Then some of the water 0.045 0.45 from source source 1. Source 1 here is seal pot wastewater. Is added to the seal pot. Wait, seal pot feed water, sorry. So seal pot feed water. Wow. Right. So from seal pot, which is S R2 wastewater, comprises of 0.1 kilogram per second. So 0.045 goes to the uh, filtration, after filtration, which is compression. Then the remaining goes back to the seal pot. So this is the uh, case study. Beta. Where is it? The case study. Oh, the next case study is mm, wait. Actually, there is a lot of case study. This is about visitor fruit juice case study using method material recovery pinch diagram. Oh, right. Put me back. Okay. Okay. So this book is uh, sustainability. Okay. Sustainability in the process industry, chapter 5, page 117. I have not sure. If I have share with you guys this 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 book. Okay, later I check. So MRPD apply to fruit juice case study. MRPD is material recovery pinch diagram. Table 5.3 shows the limiting water data for a case study involving the production of fruit juice. The water amount are expressed in cubic meter cube per each batch. There is a start time and end time for each water sink and source. TS is start time, TT is the end time. Prior to water recovery, fresh water and wastewater amount are calculated to be 96 meter cube and 84 meter cube respectively. So this is the uh, current freshwater and wastewater needed used by this production before the before the water recovery, pinch water pinch analysis or mass pinch analysis. For this case study, three assumptions are met in order to simplify the analysis. The batch process is operated repeatedly on a yearly basis. Wait. Therefore, the process behaves as if it is operated in continuous mode. It has been shown elsewhere that a repeated batch operation achieve the same flow target as for equivalent continuous operation. Second one is unlimited water storage tank is always available, thus water can be stored for later use. The third assumption is water recovery is always carried out between two consecutive batches. In other words, water source in an earlier batch will be sent to water storage tank before being reused or recycled to the water sink of the next batch operation. Given this assumption, any established targeting technique for continuous process can be used to identify rigorous water target for the case study. For purpose of this example, MRPD is used, illustrated in this figure 5.4, and the network that achieve the MRPD derive water target. So for this mass pinch, it's based on flow rate and kilogram. Kilogram, yeah. But they didn't provide the data, okay. So Sing 1, Sing 2 until where is it? Sing 5. This is the first step. You need to uh, how is it? Arrange it. Yeah. Not necessarily SK2. Sing 2 will be after Sing 1. It is it based on the uh, because this is based on ppm. Should be based okay. This is based on ppm, not ppm. Kilogram, okay. So arrange it after SK1. So which one that comes first is lesser than SK2 and SK5 and SK6, SK3. The mass, the mass. Sorry. So from here, this is a method called. This is the second method, sink source composite curve, yeah, where you plot sink first and source, then you shift the source until it uh, overlap with the sink. So here is your pinch, and after the pinch is the wastewater, while before the source starts here. So SK1, SK4 is using a fresh water source. So as shown in this figure, the minimum freshwater demand is 35 meter cube. The wastewater flow is 23 meter cube. It already mentioned that they use 96 freshwater and 84 wastewater. Therefore, by doing the water recovery, they can save 63.5 and 72.6% of freshwater and wastewater respectively. Uh, this is the network design. So freshwater based on the uh, MRPD or for from 35 meter cube of freshwater, 20 goes to SK1. I'm not sure what is the SK1 here. SK1 is referred to some process or unit operation. Yeah. SK1, then SR1 20 goes to the ST1. Don't know what is the ST1. They didn't specify. It's 26. So 26 plus 9 is 35. Yeah, see, 0.7 plus 0, 9, 8.3 is 9. So 35 freshwater used by SK1. Another SK1, SK5. Hmm. So for I will share with you the mm, most of the book I have. I'm using 3 to 4 book today. For those who have not make your attendance, wait, can do so now. Yeah. Take your attendance first. I think that's all for this class. Uh, next next week next week we learn about process integration opportunity assessment, integration concept, and next week it's how to use grain composite curve with the case study. I'm not sure why they put it integration concept later than the mass integration strategies. Hmm. Because process integration, its subset is the mass integration, but it's okay. So thank you. If you have any question, you can ask, or later you can drop me email or contact. My email is wait, it's in the chat there. So thank you.
Thank you, Doctor.
See you guys next week.